when we do time-dependent problems, what we end up doing is quite literally stepping through time. So we would start off with something like an initial condition, take a time step, take another time step, so on and so forth. A really important feature for that is adaptive time stepping, where the software is going to consider how much your problem, how much your solution has changed from one time to another, and then adjust the time step accordingly. So this is really important throughout a lot of physics because what happens is that you start off with phenomena that happen very quickly and require a very small time step to resolve, but then eventually smooth out as time progresses, and now you can get very large time steps. So this is the case in today's tutorial. This is week 3, day 2. We're looking at diffusion through a porous medium. And what we have in the initial condition is all of our concentration, which is stuck up on one side. There's a very strong gradient here. And the first few times, it's going to very quickly start to smooth out. But then as we approach steady state, it's going to be taking a lot longer for it to reach that infinite time. Is what steady state is. Of course, we don't actually go to infinity in the software, nor would we want to. Now, one of the ways that you could do this is by changing your output times and have it bring that down and dial it down to very small time steps. The problem there is that now you're kind of recording very small time steps when nothing actually is happening. So you don't really want to do that. Okay, there are more elegant ways that I'll show you today. So the idea here, we're going to dive into some of the more advanced settings and concepts in COMSOL and computational multiphysics in general today. So open up your log tab here. When you go and you compute your problem, it's going to start populating your log. Okay, every line here is going to be a separate solution calculation that the computer has taken. Okay, so here's the first one, here's the second one, so on and so forth. And sure enough, it's taking very small times. This column is your time, here's your time step. It's taking very small time steps right at the beginning as it's resolving that very fast gradient. But then as time progresses and you're approaching the steady state, it's taking much longer ones, which is what you want, which is what the adaptive time step is. Okay, now look into the next column where it says out here. Out is where you actually are recording the solutions. Okay. Now, this is different. What you notice is that the times that you're recording the solutions are not necessarily the times that you're actually calculating the solutions. It's pretty important because sometimes, even though you want the computer to adapt your time stepping to resolve interesting features, you don't necessarily want to save all that information into your file because then your file gets very large. So it implies this kind of separation between calculations, which is each of these lines, and the times that you're actually recording. If you look down, by that logic, you might be scratching your head at this point, because what I'm saying is that the computer has calculated this time, and it's calculated this time, but it's outputted a completely different time. So how did it get that information? Right? We're going to have to dive into the settings here. So go to your study, time dependent. Here's where we've defined the range of time steps that you want. Drill into the solver configuration, solution 1, and look for the time-dependent solver item. When you click it, the first thing that you're going to see is that it's been defined by step 1 time-dependent. Okay, there's a little bit of redundancy here. So, for example, we're not able to change the output times, and that's because we've already set them up here, and it's just been copied down here for our own information, basically, and for reference. Right below that is the times to store, and we've said output times by interpolation. Okay, and that's the answer to the riddle here. These time steps were actually taken. This output time, 2 milliseconds, 4 milliseconds down here, that's actually been calculated by interpolation between the ones on either side, and I think it's actually a smoother interpolation, so it considers a bit more. But what that means is that the output times that you're seeing in this mode have not actually been explicitly calculated, which is just something to bear in mind. If you want to see what the computer sees, then click on this down arrow. This is pretty self-explanatory. You can store the time steps taken by the solver closest to the output times if you want. My personal favorite is to go for the time steps taken by the solver. There is an option, another option has appeared saying that you can only store every nth step. May as well keep that as 1, my opinion. Hit compute again, and now when you look at the output file, right, when it completes, every single calculation step that it's taken has been written to your solution file. When you go and view the solution, now you can go in and select all of these. So you can go through very fine time scales and see, yes, your gradient has grown as you would expect, which is very nice. Now, there is something a little bit funny that you might notice when you're contemplating this. Okay, this is our output time range from 0 to 100 in increments of 2 milliseconds. Right, our initial time, time 0. Our final time is 100 milliseconds, 0.1 seconds, right? But what happened to that 2? It turns out that that 2 is completely ignored at this point, which is a little bit funny when you think about it, but there it is. The idea behind this is that the solver is taking its time steps according to the tolerance, and it's just used your initial condition and your final condition. But what if you, as the designer of this problem, realize that there's something going in at some kind of frequency, and you want to slow the solver down because you don't trust it to pick those up just through accuracy alone? You want to forewarn it. To get this, we have to drill a little bit deeper still. Go down here to your time stepping section and expand it. The first two options, solver type and method, we're going to be talking about in third-year numerical methods, but the key one here is going to be your steps taken by solver. By default, it's going to say free here, and free means carte blanche. The software is completely empowered to take whatever time step it deems necessary according to the tolerances that either you have set or the physical interface has set. It's one of these default arguments too. Okay? If you don't want to use that, you have a few other options. First one is going to be intermediate. And what intermediate means is that for every interval in your output times here, so 0 to 2, 2 to 4, 4 to 6, 6 to 8, thou shalt take at least one time step. Okay, so at the beginning, where the time step is naturally very small, no big deal. At the end, where the time step wants to be a lot bigger, it's going to start ramping that down. Hit compute. And when we look at the log file, there's nothing, nothing, nothing. Okay, and now all of a sudden, we forced it down to a smaller time step. Now remember, intermediate means that you have to take at least one in that interval. Sometimes it just means that it just takes to the next interval because that's what it amounts to. But when you look at the smaller times, for example, 0.002, right, isn't taken at all. This one is just taken on one side and then the other side. Let's say you actually wanted it to necessarily take the time steps that you specified. What you would have to do then is, instead of intermediate, go to strict. And strict says, thou shalt take exactly what I told you to take, plus whatever else you want in the middle. But whatever you output, you have actually calculated. Hit compute. And sure enough, even at the smaller time steps, oops, it's trying to scroll on me here, right? Now it has actually taken 0.002, 0.004, as well as the other ones in between. So it still has that freedom to respect the tolerances, but now it's actually conforming to the time steps that you've taken. This is actually my typical configuration personally. I like to output every time that it's taking, as well as having it necessarily match up to the time steps that I've imposed on it. I haven't found it's such a big problem about file size, which is concerned with that, because typically the file size is going to be small anyway, or I'm doing a large simulation, which takes a long period of time, in which case I want to see what times the computer is actually picking up to. Okay. The last one, just for completion here, under strict, is manual. Manual effectively turns off the adaptive time stepping entirely. You can give it whatever you want. In this case, we're just saying, just do a time step of 0.01. Never mind the range at all, right? And sure enough, it completes very quickly, and it takes exactly 0.01, but there's no error control here. And that's the problem, especially for problems like this, which are relatively small. I mean, really, we're talking about the matter of minutes. And for larger problems, again, you're calculating it in more detail. It's a more expensive run. You really want that temporal detail.